Hi everyone, today I will talk about my work which is lumbar and pelvis statistical shape model to characterize population shape variations. Degenerative disc disease is a major musculoskeletal disorder where the disc may dry out, thin or crack, causing numbness, weakness in the patients. Patients who fail to find relief with non-operative management, they are often considered for spinal fusion surgery. But due to incorrect placement of the implant, 40% of the spinal fusion surgery fails, and out of which only 25% of failures might be reversed. Generic models are not sufficient enough to provide detailed morphological information of the spine, so a population-based model such as statistical shape model is needed, which can predict the patient's specific bone shape with simple measurements. In this study, I have developed two statistical shape models, one with bone measurements and the other one without bone measurements. The objective of my work was to compare the prediction accuracy of the statistical shape model with and without bone landmark measurements. For my methods, at first, 70 de-identified CT scans were collected, and then all of the bones were 3D reconstructed using mimics, and then template measures were built for each vertebral level, sacrum and pelvis, and fitted and aligned to the template bone surface for nodal correspondence. Then a principal component analysis was performed on each bone level. Then, based on the PCA outcome, we extracted weights from 70 principal components and imported it into a partial least square regression algorithm. The input for our partial least square regression algorithm for our first model was only age and gender and weights for each PC, but for the second model, it was weights for each PC, age, gender, and the measurements of such as height for the vertebrae, length and width of the vertebrae. For the pelvis, it was posterior superior iliac spine distances and anterior superior iliac spine distances. And for the sacrum, it was sacral plateau length and width. And then to understand the predictive power of our models, we did a leave one out validation analysis with and without bone measurements. Then we have obtained the predicted surface mesh, and the prediction accuracy was quantified by computing the root mean square error of the Euclidean distance and the die-score quantified between the SSM predicted shape and the CT reconstructed shape. These are some SSM prediction results from my models. In every model, the red is the original shape, the blue is the shape predicted with landmarks, and black is the shape predicted without landmarks. In figure 1, you can see for the L4 vertebrae prediction, the blue model, which is the shape predicted with landmarks, did a much better job than the black model, which is the shape predicted without landmarks. For the blue model, it predicted the articular process and vertebral body similar to the original shape, but for the black model, it was much smaller. From my figure 2, we can see that for the pelvis shape prediction, the shape predicted with landmarks and the shape predicted without landmarks did a similar job. But for the sacrum shape prediction, the shape predicted with landmarks did a better job in predicting the superior articular processes of the sacrum. So the root mean square error for our vertebral models with landmarks were 1.58 plus minus 0.4 millimeter, and without landmarks it was 2.4 plus minus 0.6 millimeter. And the RMSE with our landmark model was similar to the other study reported by Hollenbach et al. Our model have the prediction capability of bone morphologies with very small error, which is clinically acceptable. So the characterizing the patient-specific bone shape is essential for representing the optimal design of fusion implant for every patient, and our model can predict the bone shape with a very minimal RMSE error and guide the surgeons in pre-surgery so that the failure of the surgery is minimized and the patients can lead a better and healthy life.